Finish the spiel. It's all right. Hello, YouTube. So, we're going to start with lesson 16.1, which is dilations. What is a dilation? A dilation is a transformation that can change the size of a polygon but leaves the shape unchanged. Okay, if I have two shapes and they're both the same exact size and shape, then those shapes are what? Congruent. Good. Two shapes that are the same size and shape are congruent. What about two shapes that are the same shape but a different size? Very good. Similar. Similar. So if I have two shapes that are the same exact shape but they are a different size, they are called similar. Okay? Same size and shape, congruent. Same shape, different size, similar. All right, so one way that we can produce a similar shape is through a process called dilation. And once again, a dilation is a transformation that can change the size of a polygon but leaves the shape unchanged. Okay, so what are we going to do? We're going to get right into it. So we're going to skip a whole lot of this and go straight to page 831. And let's take a look at these two shapes here. So we notice we have triangle ABC, and then we have this triangle here, different size but same shape. The triangle ABC is my original shape. This triangle here is my dilated shape. And we notice that it's not just ABC, but there's what's next to each one of those letters? What is it? Little apostrophe, right? So in Mathanese, we call that prime. So I don't say A apostrophe, but I call that A prime. I don't call this B apostrophe, I call it B prime, not C apostrophe, but C prime, okay? So the shape that has the primes next to it, or the apostrophes next to the letters, that's the dilated shape, okay? They'll always be the same letters. The original shape will not have the primes. The dilated shape will have the primes. Pretty clear? Okay, so let's talk about something. That's a dilated shape. Let's talk about something called scale factor. Now, before I specifically ask you for the scale factor, I'm going to ask you one thing. Is the dilated shape bigger or smaller than the original shape? Smaller, right? So if the dilated shape was, so I'm talking about scale factor, and scale factor is a number, right? It's a number. And if I were to say that the dilated shape was the exact same size as the original shape, what would you say the scale factor would be? 1. 1. Right? 1 to 1, scale factor is 1. Same size, it's a scale factor of 1. If it was bigger, for instance, if the dilated shape was bigger than the original shape, what's an example of what the scale factor could be? 2, 3, 4, right? Or in other words, it would be bigger than 1. Okay? So the scale factor, if the dilated shape is bigger, then the scale factor is bigger than 1. If it's smaller, then what would it be? What's an example of a scale factor for if the dilated shape is smaller, such as what we have here? Less than 1. Very good. Now, just taking a look at this, how would you talk about the size of this as compared to that? What would you say? Guess. Smaller. Half, right? This is half the size of that? Sure. Yep, it actually is. So the scale factor would be 1/2 for this one. But let's give it a specific definition. I'm going to give you two definitions for this because both are equally accurate. A scale factor is the ratio of the size of the dilated shape over the size of the original shape. Does that make sense? So for instance, if this is like half of it, it's going to be 1/2. Okay? Half the size, it's 1/2. If it's twice as big, the scale factor would be 2. Does that make sense to you guys? Okay. But now let's get a little bit more concrete with this. Let's get a little bit more concrete. So what I'm going to ask you guys to do is do a little bit of drawing. Before I tell you to do the drawing, though, I will tell you that from here on out, you're going to need a protractor in this class. Okay? Hopefully everyone knows what a protractor is. If not, you can go ahead and take a look at this picture here that I have conveniently pulled up. This is a protractor. Is that clear? Yes, it's a clear protractor. Get it? Ha ha! Bam!
Oh my
On it.
gosh.
Yes, it's clear. It's a clear protractor. A protractor. Why is it a protractor that I'm asking for, not just a ruler? Well, a protractor is multifunction. It operates as a straight edge for drawing, a ruler for measuring length, and then this protractor for measuring angles, right? This arc for measuring angles. Okay? So you guys are going to have a protractor, not by next class, but by the class after that. If you don't have it by that time, it's going to start affecting your grade. Okay? What that's going to look like is I'm just going to take points off your homework. Yes, ma'am. Question? Oh, thought you had a question. You're good. So, is that clear? You guys need a protractor. If I were you, I'd get it immediately just so I don't forget. I probably would be the person that would forget in math class, so I'd write myself 12 reminders. Okay? So, just remind yourself, get a protractor. Okay? You're going to need one. Why are you going to need one? Because we're going to do lots of measuring and angle drawing and stuff like that in this class. With that said, if you have a protractor right now, cool, pull it out. If not, pull out a credit card or something else that you can use as a straight edge for drawing. So pull that out now, please. Whatever you got is cool with me. Just pull out a straight edge. Yeah, no card, anything. Anything's fine.
That chip back straight line?
Nope. Any straight edge will work. Stop flexing.
Isaiah's flexing.
Okay, I hope you guys all have your straight edge out. This is what you're going to do. The first thing you're going to do is you're going to line your straight edge up such that it goes through point C and C prime. You're going to draw a line from C through C prime and draw it out long like that. Okay?
How long?
Just as long as you pretty much can. Okay?
I'd say that's pretty long. We don't have it.
I know.
That's crazy.
What?
That's wild.
All right. Shh. All right. Now, shh. Next thing, look, class, you're going to line it up with B and B prime. Draw a line from B through B prime and out, just like that. And you should notice that they intersect quite clearly. And the last thing you're going to do is draw a line through A and A prime, and you're going to make an observation. Tell me what you observe. What was that? What do you observe about these three lines? They all come to a point. They all intersect at the same point. That is called a point of concurrence. And that point of concurrence, in this case, is called the center of dilation. Very good, Skylar. It's called the center of dilation. It's a point of concurrence. Whenever you have more than two lines intersecting like that, it's not called the intersection point. It's called the point of concurrence. Okay? So it's a point of concurrence, and this one is called the center of dilation. Why? Because this is the center about which the dilation is performed. Yes, sir.
Does every pair of triangles or shapes have this?
Every pair of shapes where one is the original and the other one has been dilated about some center of dilation will have this exact kind of characteristic where you can draw the lines through and it meets all in one point. Good question. Okay, now, I'm going to create a new definition for scale factor. And in order to write this new definition for scale factor, I'd like us to make an observation. What do you guys observe about this distance from A prime to the center of dilation as compared to this distance, the distance from A to the center of dilation?
Isn't it half?
It's half. The distance from A prime to A is equal to the distance from A to the center of dilation. But if you compare the red to the green, if you compare the red to the blue, it's equal in this case. But if you compare the red to the green, guess what? The red is half of the green, which means, wait a second, what else was a half in this case? The scale factor. So the definition for scale factor is, it is the ratio of the distance from the center of dilation, the COD, to the dilated shape over the distance from the center of dilation to the original shape. Does that make sense? Let's take a look. For instance, if I said to you that this red was 1 inch, then this green would be 2 inches, and it would be 1/2. You see? Does that make sense? Or, for instance, if the red was like 3 inches, and the green was 6 inches, well, it would be 3/6, which simplifies to 1/2. Does that make sense? You guys see? Now, one thing, that's true. That's also true for all the ratios. It's not just 1/2 here and then like 1/3 here. No, it's 1/2 here, 1/2 here, and 1/2 here. Does that make sense? Okay, it's 1/2 for all. That ratio, that scale factor is true for all. Now, if it's not true for all, then guess what you don't have? A dilation. If it's not true for all, then it's not a true dilation. It's like transformed in a weird way. Does that make sense?
Yes.
Okay? So whenever you have a true dilation, this goes back to Skylar's question, you will have a true center of dilation, and the ratios will always be the same. Is that pretty clear? Okay, so now that you guys are aware of that, go ahead and do the same thing for number 8 where it says your turn. Okay? So you're doing the exact same thing. And in doing that, see if you can determine the scale factor by looking at it. I'm going to do it along with you. Most of you guys should be done at this point, or close to it. So I'm going to draw my lines. Guys, I'm just such a big fan of like precise drawing. Like it just makes me so happy. So like when you guys do these drawings, like the more neat that you can be, like, you know, I've got a 4-year-old daughter, and like right now we're teaching her to like use scissors, right? Most of you guys can use a pair of scissors, right? You know, hold a pen correctly, though a lot of people do actually have struggles with holding pens correctly like their whole lives, so it's not that abnormal of a thing. But you may maybe have trouble with like holding something and drawing perfectly straight and keeping your arm steady and things like that. When you practice drawing in a class like math, unless you're an artist, this is probably one of the only times that you're going to be doing precise drawing like this, where you're being asked to like be very precise. So take it as an opportunity to just practice your fine motor skills, which correspond to greater brain strength, which corresponds to greater brain health. So be healthy, y'all. Eat your Wheaties. Yes, ma'am. What's the correct way to hold a pen? Well, there are variations, but like you see a lot of people that, for instance, will like hold it like this, right? You should hold it like this. This should be your main way. These two fingers, and then it rests like on this. That's the main. These are the two, because it basically should be a fine motor skill with your thumb and your pointer finger. Right. How do you hold it? Yeah, so you hold it like this. Right. Yeah. Yeah. So
There we go.
here's the thing. If it's fine for you, that's fine. If you have good handwriting and you're happy with your handwriting, that's fine. So, but if you don't, if you feel like your handwriting could be better, or sometimes it's shh. Look at these guys, just jokers, not even paying attention, thinking you're in your own world. Stop it. Okay, when you're holding your pen, sometimes if you hold it incorrectly, it can take you longer to write, which can then make it frustrating to do things like writing essays or things like that. So anyhow, that's just a thing. You should be holding your pen basically like this. Sometimes like I'll hold it like this, like it's different, you know, but like if you are holding it like this, realize that that's not necessarily the most ideal, or like this. It's fine. There's nothing wrong with you. Your girls are like, there's nothing wrong with me. There's nothing wrong with you. You're good. You're good. It's just maybe it's something to experiment with. Anyhow, so shh. That's all on YouTube. That's great. Okay, so, all right, this is my center of dilation right here. This is my center of dilation. Okay. Now, what would you guys say is the scale factor of this one? First off, is the dilated shape bigger or smaller?
Smaller.
So the scale factor should be
Less than
1. What would you guys say? Guess it.
a third.
A third. Cool. It's a third. It's a third. If you look at this distance, it's like, yeah, 1, 2, yeah, 1/3. Now, we've just been eyeing it out. How could you know for sure? Measure it. You can measure it. You can figure out, like, is it 1.2 inches and then, like, 3.6 inches? Oh, yeah, it's 1/3. You understand what I'm saying?
Yes, sir.
Okay, so you can always measure it. Any questions on this? You guys see the visualization of it? Okay, now check this out. But there's more. Look, check this out, guys. So here's this cool Desmos tool where you can actually see dilations in action. So this black is the center of dilation. The blue is the original shape. And notice I can change that. And the red is the dilated shape. Okay, and notice, look, if the center of dilation is wherever it is, doesn't matter. If the scale factor is 1, it just sits right on top of each other. It doesn't matter where the center of dilation is, right? If the scale factor is less than 1, bam, it's smaller. If it's greater than 1, look, it's bigger. You see that? Now look, if I put, for instance, the center of dilation in the triangle, look what happens. Oh, well, that was weird. Check it out. Look, see? It like kind of grows out of it, right? That's cool. All right. And what if the center of dilation is on a vertex like here? Well, look, bam, that vertex stays at the same place basically, right? You see that? Doesn't matter what the scale factor is. That vertex stays at the same place. Doesn't matter if I make it really big or really small. You see? That's pretty cool. And then you can kind of just play around with it, and then you see the perspective. Does anybody see like a 3-dimensional shape in that?
Yeah, but like that does. But not. Yeah, it's kind of. But no.
It looks like an ice cream.
There you go. There you go.
Getting bigger.
Right?
Oh yeah, that definitely.
Right? Like, can you guys see like the 3-dimensional shape in that? So it's cool. It's like you guys, if any artists in here, you could talk about like the vanishing point of perspective, right? Like you could talk about vanishing points, and you would have like the same vanishing point for every line. And that's pretty cool. But yeah, I don't know, man. It's pretty sweet. So that's math for you. I think it's also really cool. One thing that I can share is like is, this kind of thing tells you information about the distance between yourself and an object, and like which angle things are pointing, all that kind of stuff. This three-dimensional information. Like if I change the center of dilation, look, it looks right now like, if you can see this with me, it looks like it's kind of coming out like that, right? Well, if I put the center of dilation like over here, now it's it's the same shape, but it's like changed its angle and direction. You guys see that? So like imagine when you're driving on the highway, right? And you see like a car or a truck, and it's like angle is going like this, and you can kind of see this three-dimensional perspective, and it's getting closer to you at this certain rate, right? And so this vision is getting closer to you, or / getting bigger, right? And your mind is instantaneously like calculating the distance between you and this truck, and how fast you're going compared to that truck, and how like, and you're just like, oh yeah, whatever, I'm just gonna switch lanes. Like the amount of complex math that your brain is just able to process without you even thinking about it is absolutely mind-blowing. So that's what God has given you. It's pretty cool. Yeah. Yes, she did. Good pass. Thank you. Okay. So anyhow, I just figured I'd share that with you guys, because I'd like you to start being able to visualize things like this and start translating it into your real life experience. Start translating this visualization of three-dimensional objects. Maybe start noticing things. Notice how this looks as compared to like this in your visual field, right? Part of math is not just like working with numbers, it's being able to process information. So some of that information is visual. I don't know, it's cool stuff. So I hope you guys can do that and grow in your abilities with that as a result of these lessons. What's your homework? Page 832, number 1 through 18. And that's all she wrote. Any questions?